Okay, thanks. So welcome everyone to the One World Probability Seminar. Today it's a great pleasure to have Vittoria, Silvestri, and James Norris. Our first speaker will be Vittoria, who will be speaking to us about plane aggregation with subcritical fluctuations in the Hastings-Levitov model. Over to you, Vittoria.
Thank you, Ilya, and thanks for the very nice invitation. So today I would like to present some results on a class of growth models which goes under the name of aggregate Loebner evolution, and the Hastings-Levitov models are a particular case of test. I can't. Okay. So I'll start with a few words of motivation. We're interested in describing growth in stressed conditions. So here is an example. This is a bacterial colony which is trying to grow in space, but we have to imagine that the nutrient in the surrounding environment is limited. And in these experiments, researchers have analyzed the growth of the colony according to different levels of nutrients, so they're going to lower it progressively. If the nutrient is high enough, we see this spherical growth, and as it becomes lower, this fingering structures appears, and the fingering becomes more evident until the disc shape is broken because the nutrient is so low. And we see this kind of ramified structures in many places in nature. Here are a few examples: lightning during a thunderstorm, corals underwater, and dielectric breakdown phenomena. And we would like to build mathematical models for those structures. So to start with, one could work with discrete growth models, and I will discuss a few of them, but then I will move on to a continuous approach. So we're going to take the view that the growth happens by aggregation of particles. And in the discrete approach, particles live on a discrete graph, which here is the d-dimensional grid, in this picture, the two-dimensional grid. And in order to specify the model, we have to specify a probability measure on the outer boundary of the current aggregate. So we sample a site according to that measure, and we aggregate the site to the cluster. In the continuous approach, clusters or aggregates will be subsets of the complex plane, and we will have to prescribe a probability measure on the boundary of these subsets according to which we aggregate particles. So in the class of discrete growth models, there are many famous models, such as the Eden model, in which particles, say we work on ZD, so we are on the d-dimensional lattice, and particles aggregate uniformly on the outer boundary of the cluster. So the probability measure that we prescribe on the boundary is just a uniform measure on all possible sites, and we aggregate according to it. Now, this is a simulation which has been done by Jason Miller of an Eden cluster, and we see that it looks quite regular, except the boundary is a bit irregular, and it looks also close to a disk, but we see some flatter regions, so it's unclear whether this large-scale structure feels the structure of the underlying graph. Now, in another famous model which falls in this class is diffusion-limited aggregation, or DLA, in which we start with one seed at the origin, and at each step we aggregate according to the harmonic measure on the outer boundary of the cluster, which means we start a simple random walk very far from the cluster, and we wait for the random walk to reach the outer boundary of the current cluster, and at the location where it reaches it, we aggregate the new particle. So the measure we're using to grow is the harmonic measure on the outer boundary of the cluster seen from infinity. And we see that the structure of diffusion-limited, the large-scale structures generated by diffusion-limited aggregation look more irregular than the Eden model. And in fact, if the cluster starts growing arms, they get reinforced because the random walkers is more likely to reach the cluster on the arms rather than somewhere else. And if the cluster leaves fjords, they get penalized by the growth because the random walker is very unlikely to go inside the fjord and manage to fill it. And this is a simulation done by Vincent Befara of DLA on Z2. And we see that here it's, at least in this simulation, it seems evident that large-scale DLA clusters see the structure of the underlying graph, which has this grid shape. And while for diffusion-limited aggregation, we know almost nothing. For example, we don't know that these clusters are not just Euclidean disks. For the Eden model, there's more literature available, and it is known that there is a limiting shape. It's known that it's convex, but it's not known whether it's a disk or not, at least in low dimension. And in this simulation, it's unclear whether it should be a disk or not. It might fill the underlying shape, the underlying discretization. And since Eden model is manageable mathematically and diffusion-limited aggregation is out of reach, we might think of interpolating between the two models. And here I would like to discuss two ways of interpolating between the Eden model and diffusion-limited aggregation. So one is multi-particle diffusion-limited aggregation, which consists in imagining that rather than having one particle diffusing outside of the cluster, like in DLA, and then joining the cluster and then adding another diffusion, we have a cloud of diffusing particles around the clusters, and whenever one of them comes into contact with the cluster, it just sticks to it, it joins it. And the limiting shape of this aggregate will depend on the density of the particles around it. So if the density is very low, you might think that you basically are doing diffusion-limited aggregation because basically only one particle is arriving at each time, and then there is another diffusion coming later on. So particle aggregate one by one. And this is a simulation of an MDLA cluster done by Alexandre Stauffer, in which the particles outside the aggregate are initiated with an IID Bernoulli distribution of parameter mu. So mu controls the density. And as you increase the density of the cloud of particles outside the aggregate becomes denser. And when the density becomes high enough, you might think that you are roughly in Eden regime, meaning that you have so many particles that at each time step, you can aggregate on all possible sides on the outer boundary, and you're just going to choose one of them uniformly at random. And so you're back to Eden model. So this is a family of models which interpolates between DLA and Eden, but it has proven very hard to study. And in fact, diffusion-limited aggregation was originally introduced in order to simplify multi-particle diffusion-limited aggregation. So it doesn't seem very promising to try to deduce properties of DLA from properties of MDLA. So we're going to take another point of view, which is interpolating between these two models using powers of the harmonic measure. So in DLA, we aggregate particles according to the harmonic measure on the outer boundary of the cluster, seeing from infinity, raised to the power 1. It's just that measure. And in Eden model, we aggregate uniformly. So that's, if you want, the harmonic measure raised to the power 0. And so you can think of aggregating according to a fractional power of the harmonic measure on the outer boundary of the cluster, seen from infinity. And you get a one-parameter family of models indexed by this power gamma, and these go under the name of dielectric breakdown models. Now, this is not a simulation, this is just a picture of physical phenomena which are believed to be well described by dielectric breakdown models. And it's hard to simulate from this kind of probability measure because you don't have this simple random walk representation that you have when the exponent is 1. So I would like to describe a class of continuous random aggregation models with the idea in mind that particles will aggregate according to a power of the harmonic measure. And these are the Hastings-Levitt models. So we're going to work on the complex plane, and we're going to build random clusters using random conformal maps. And our initial seed, our initial cluster is just a unit disk. I will comment at the end of the talk on other initial shapes. So we want to aggregate particles to the unit disk. And if we want to mimic a diffusion limited aggregation, you might think of starting a Brownian motion from infinity, very far from the cluster boundary, letting it run until it reaches the boundary of the unit disk and aggregating a particle at the point where it hits the boundary. And well, at the beginning, it will hit uniformly around the circle. So let me just rotate things so that it hits at angle 0, at 1. And what do we mean by aggregating a particle? Well, we're going to fix a shape, which in this talk will just be a slit, but we can work with more general shapes. Once we fix a shape such that the unit disk union that shape has a complement which is simply connected in C with the infinity point, then there is a unique conformal map, F, which maps the outer boundary of the unit disk to the outer boundary of the structure, unit disk union the particle. And well, in fact, a priori, we have many possible choices for this map, but if we prescribe that the map fixes infinity, and if we prescribe that the derivative at infinity is a real positive number, there is a unique map which does that. And so in order to describe this cluster, we will equivalently describe this map. Now, this first one is just deterministic. You fix a deterministic shape and you can write down the map. For the slit is explicit. It's not particularly nice, but it's explicit. And if I put these two requirements together, this tells me that around infinity, the map f of z looks like some positive number, which I called e to the c because it's positive, times z plus an error, which is order 1. And this c here seems like a parameter which just comes out of this requirement, but in fact will play an important role in our discussion. And I would like to give a geometrical interpretation for C. So take a point Z outside your cluster with one particle and start a Brownian motion from it. Forgive my picture of Brownian motion. And wait for the Brownian motion to hit the cluster. So it either hits the cluster on the particle or on the boundary of the unit disk, and you stop it there. Call this stopping time T, capital T. And you look at the expected size of the logarithm of the modulus of BT. So you see that if the Brownian motion hits the cluster in a point which does not belong to the particle, you just get 0 contribution. And if it hits the cluster on the particle, you get a positive contribution. So this value is going to be positive. And then we're going to send z to infinity. And this limit will give us C. So we should think of C as measuring the size of the particle. And it's a way of measuring the size of the particle, which we can read off the conformal map. We just look at its behavior at infinity. So it's particularly handy in our setting. And this is often called logarithmic capacity or simply capacity of the particle. And if the particle is simply a slit of diameter d, just to tell you how C behaves, when d is small, which is the regime we're going to look at, small particle limits, d scales like d squared. So the square of the diameter of the particle up to multiplicative constants. If you think about D as being a small disk, then C scales like the area of the disk. Okay, so this is the way we're going to measure the size of particles. And applying F is what we mean by attaching one particle to the cluster. And now we want to keep on going. We want to attach more particles. So let me call this F1 to encode that it grew the first particle. Now I'm going to start an independent Brownian motion from infinity, because if we want to mimic diffusion limited aggregation, we have to start, well, simple random walks in the discrete settings and Brownian motion in the continuous setting, and wait for them to hit the boundary of the cluster. That gives us a location at which we would like to attach the next particle. But now describing the distribution of this location is not trivial as before, because this cluster is not a disk anymore, and we can't simply use invariance under rotation of Brownian motion. But one thing we can use is that the Brownian motion is conformally invariant. And this map F1 is conformal. So if we want to, if we for a second forget that we had already attached one particle and map it out by applying the inverse of this map F1, which takes the outer boundary, the outer domain of this cluster, and it maps it to the outer domain of the unit disk, and it takes this slit and it maps it to this red arc, then this will map the Brownian motion to another curve, which is again a Brownian motion, because Brownian motion is conformally invariant. And here it's easy to describe the arrival location. It's just going to be uniform around the circle. So we're going to choose an independent uniform angle, and we grow a particle there by applying a map F2. Now, if we know how to grow particles at 1, we know how to grow particles everywhere around the circle, because we can just conjugate with the rotation. We first rotate to bring the point that we want to attach at to 1, we grow the particle and then rotate back. And now we have to remember that we had already attached one particle, so we grow it back by applying the map F1, which takes this red arc and it maps it to the original first slit. But now this F1 acts on the second slit that we attached, and it deforms it. And if you compose these maps together, you realize that you simplified F1 composed F2. And now we can keep on going. We want to aggregate a third particle to the cluster. So we start an independent Brownian motion. We wait for it to get to the boundary of the current cluster. And in order to describe the arrival location, we're going to, first of all, forget that we had already attached two particles by mapping them out via F1 composed F2 inverse. The Brownian motion is mapped to a Brownian motion, and this is going to hit uniformly around the circle. So we choose a uniform angle, attach a particle there via another random map F3, which is again a conjugated version of the deterministic map F, and then we grow back the first two particles. This will grow the first two particles as they were, and it will have the effect of deforming the third particle. And so if we compose these maps together, we realize that we just composed F1 with F2 and F3. And so to attach n particles, we simply compose n conformal maps, F1, F2, up to Fn, which are obtained by a deterministic map, which grows just one particle at 1, conjugated with a random rotation. And in order to describe uniquely these maps, I have to tell you, well, the attachment angles, so the points of arrival of Brownian motion around the unit disk, which are this theta k, and what we've seen in the construction of the model, which will just be IID uniform angles around the circle. And one thing which I haven't commented on is the particle sizes. So what should be the length of the slits that we attach when we grow our particles? Now, to start with, you could think of attaching slits of deterministic length. So you fix a constant c, which, as I said, we're going to think of as being small, because we will look at small particles compared to the diameter of the unit disk. And so you prescribe that all of your particles, when they grow around the unit disk, they grow up to capacity c, which will give you a diameter which behaves like square root of c. And well, this gives you particles of a deterministic size in this left picture. But then when you attach the nth particle, you attach it to the unit disk, and then you map it back to the actual cluster by growing back the previously arrived particles. So this slit gets deformed and it goes into this, it becomes this blue curve. And you can work out the distortion factor. You can work out how the length of the slit changes under this map. And in order to do the exact computation, you would have to integrate the derivative of the map you're applying in modulus along this curve. But if we think of particles as being small, we can apply the mean value theorem and say, well, the size of the particle, the diameter of the particle is going to be multiplied by this factor, modulus of phi prime at the attachment point. And since the capacity behaves like diameter square, we get a square here. Now, this factor is inversely proportional to the harmonic measure on the cluster boundary. That's an easy computation using conformal invariance of Brownian motion, which means that if you attach at points, can you see my pointer? Yes, okay.
Yes, we can see it.
Okay, so if you attach at points like this one in which you have high harmonic measure, meaning the Brownian motion is likely to hit the cluster at that point, then this factor is going to be small because it's inversely proportional to the harmonic measure density. And so the particle will become small. You will attach a small particle. Whereas if you attach at points where the Brownian motion is unlikely to hit the cluster, for example, this point here, you will attach a large particle because this factor will be large. And so this has a regularizing effect, meaning that it's more difficult to grow arms because they will get more harmonic measure, and so the particles attached there would be smaller. And it's easy to fill fjords because if a fjord is a region which has low harmonic measure, and so if you happen to attach around there, you will attach a large particle. And this is not what we see in diffusion limited aggregation, at least in the discrete version of diffusion limited aggregation. So this is, it's just a feature of using conformal maps. It's a feature of the construction of the model, which we would like to compensate for. And so the physicists Hastings and Levitov in 1998 proposed to give up the idea of attaching particles of deterministic size and instead attach particle of random size. And the random size should be adjusted so that you get exact cancellation in the actual size of the cluster, of the particle in the cluster. Mind you, these are all approximations. These are all heuristic arguments. Okay, I use the mean value theorem. I use that C is small. So they propose to attach particles of capacity Cn. Cn should be the size of the nth particle, which is given by some factor C, which we think of as going to 0, divided by this distortion factor, which, remember, is inversely proportional to the harmonic measure on the cluster boundary, close to the attachment location. And this has the effect of giving particles of roughly constant size in the actual cluster. And they say, well, rather than insisting on exactly compensating for the distortion, we can partially compensate for the distortion by introducing an exponent alpha here, which will have the effect of growing particles of roughly this size on the actual cluster. Okay, so this gives us a one-parameter family of models, which go under the name of Hastings-Levitov models, indexed by alpha, this exponent. And when alpha equals 2, this is a continuous analog of diffusion limited aggregation. When alpha equals 0, we just accept the conformal distortion, which regularizes the growth. And in between, we should interpolating between regular growth and diffusion limited aggregation type growth. And you can try to work out the rate of growth on a point on the cluster boundary at a given exponent alpha. So if you take a point Z here on the cluster boundary, it's handy to parameterize the cluster boundary using the unit circle. So I'm just going to parameterize it by saying that a point Z is just the image of a point on the unit circle under the map that grows the cluster. And you can try to work out the rate of growth at this point Well, the rate of growth, this is very heuristic. It's roughly the rate at which particles arrive at that point times the size of the particle that you grow there. And the rate of arrival is, well, the harmonic measure. And so you get the same distortion factor we saw earlier, raised to the power -1, which, well, this is just representing what I was saying about that factor being inversely proportional to the harmonic measure, to the density of harmonic measure on the cluster boundary. And the size of the particle you attach, we've seen that it's given by this. The 2 comes from the conformal distortion, and the alpha, it's the compensation coming from random particle sizes. And so what this tells you, if you just sum up the exponents, you get this C, well, C is something small, times this factor here raised to the power 1 minus alpha. And I said that the harmonic measure is inversely proportional to this factor, so this is the power of the harmonic measure. It's the harmonic measure raised to the power alpha -1. This is a very heuristic computation to persuade you that this cluster should grow according to a power of the harmonic measure. And you see that if you plug in alpha equals 2, you get power 1, so you get diffusion limited aggregation. And in general, well, when you have alpha below 1, you have a negative power of the harmonic measure. So it's difficult to grow arms and it's easy to fill fjords. So you expect a regular behavior. And when the power of the harmonic measure is positive, you expect an irregular behavior. You expect macroscopic fluctuations because arms will get reinforced and fjords will get penalized. And this is these are a few simulations done by Alan Sola and Amanda Turner on Hastings-Levitov clusters as alpha goes from 0 to 2. So this is alpha equals 0, alpha equals 1, in which clusters should grow roughly uniformly on the boundary because it's the harmonic measure raised to the power alpha -1, so to the power 0. So this is, if you want, the continuous analog of the Eden model. Clusters grow roughly uniformly. When alpha equals 2, we're attaching according to harmonic measure particles are roughly the same size, and we get an analog of DLA. And between 1 and 2, we get these dielectric breakdown models growing according to a fractional power of the harmonic measure. And the physicists conjecture that you should get nice disk limits with microscopic fluctuations below 1 and macroscopic fluctuations above 1, which is what they refer to as turbulent behavior. So today I would like to discuss the behavior of these models. And before I go into the results, let me just mention that in order to work on these models, well, we have to introduce a regularization parameter here, sigma, because we don't want to evaluate the derivative of this map phi exactly on the boundary of the cluster. Now, the boundary of the cluster is very irregular, and the derivative of this map will be even worse. And when we determine sizes of particles, we don't want to divide by 0 or by infinity. So we're just going to move a little bit away from the boundary of the cluster. So this regularization parameter sigma has the effect of, looking at the cluster as if instead of this black complicated structure was this nice red curve. And clearly, as we think that as sigma goes to 0, this regularization should not matter, but in fact it turns out to matter very much, the speed at which sigma goes to 0. Now, the smaller sigma, the closest you are to the boundary of the cluster, so the more irregular this distortion term is, the larger sigma is, the further away you are from the boundary of the cluster, and the nicer is this map phi prime. And the sigma we would like to work with ideally would be, well, on the scale of the diameter of the particle. And the diameter of the particle, we said it scales like square root of c. So ideally, you would like to send sigma to 0 like square root of c to see the single particle. if you want to see an averaged effect of particle arrivals, you will take sigma to be just larger than that. Okay, and the first theorem I would like to present is a result by James and Amanda on Hastings-Levitt models in the case alpha equals 0. So if you look at the definition in HL alpha, Hastings-Levitt with parameter alpha, there is this complicated distortion factor which makes the analysis hard because the size of the case particle arrived depends on what happened in the process in the first k-1 arrivals. It depends on what the cluster looks like around the arrival point. So it's complicated to control this factor, except if alpha equals 0. That's the case in which you just accept the conformal distortion and this factor is just not there. So you're composing IID maps, the angles are IID uniform and the particle sizes are just deterministic. So in that case, James and Amanda in 2012 proved that if you look at your random map, which grows the cluster up to the nth particle, that's uniformly close to a map which simply grows a disk around the origin. As the number of particles goes to infinity and goes to infinity, the size of each particle goes to 0, C goes to 0, such that the total size of the particle, the total capacity of the cluster, goes to a positive finite number, which we call T. So this is what we refer to as the small particle limit. And in this limit, the map simply converges to, well, the map that grows a disk around the origin with radius e to the t, because C is close to NC. And this is true uniformly away from, this is true on compacts bounded away from the unit disk, but in fact they can even let R approach 1 slowly enough, as long as it approaches 1 slowly enough. And the result doesn't need slit. You can choose particles which are more general, and it works within a large class of particles. So in that sense, it's universal with respect to the particle shape. So in order to visualize this result, I always like to show these pictures. These have been made by Erin Jackson, who was a student of Nathaniel Berestiki in Cambridge from 2012 to 2016. And what Harry did here is he took the unit circle and he took concentric circles slightly larger than the unit circle. So with the radii strictly larger than 1, and he mapped them via the map that grows the cluster. The map that grows the cluster is defined outside the unit disk, so it's well defined on these circles, and it maps them to these red curves. These are 20 curves. And you can see here the evolution of these curves under the cluster growth. So you see that if you were far away from the unit disk, you get mapped to nice circular curves, but they look pretty circular. Whereas if you were close to the unit disk, you still feel the cluster boundary and you get mapped to these curves, which are quite irregular. And the result by James and Amanda says that no matter what the radii of these curves are, as long as they are fixed strictly larger than 1, all of these red curves will converge to larger circles. And in fact, they say you can even shrink the red curves towards the cluster as the cluster grows, as long as you do so slowly enough. This is what I meant when I said you can let R go to 1 slowly enough. And in the same paper, they proved that these clusters also have an interesting internal structure. So this is a picture taken from their paper. You can think of fixing finitely many points inside the cluster. And well, either they are on the cluster or you look at the point closest to them, which is on the cluster. And given these points, you're going to trace back their ancestry. So each particle is attached to one unique particle, which is the father, which will have a father itself, and so on. So you can trace back the ancestry of particles back to the unit disk. And this is, you get random curves, which are called fingers on their paper. And you can think of instead doing the opposite operation. You starting from these points, you think of having a rope which are pulling from the outside of the cluster, and if you pull the rope, which will give you the shortest way to exit the cluster from that point, and this is what they call gaps. So you get a family of random curves, and the fingers are coalescing, meaning that if the ancestry lines of two particles at some point meet, well, they're going to stay together up to the unit disk. So they're coalescing backwards, and the gaps are coalescing forwards. And what they proved is that, well, if you unfold the disk and you look at the cluster in logarithmic coordinates, the fingers converge to backwards coalescing Brownian motions, and the gaps converge to forward coalescing Brownian motions. So this is a finite dimensional distribution convergence to what is known as the Brownian web. And this describes the internal structure of these clusters. Okay, this is just to tell you that not only what happens outside is interesting, they also have a rich internal structure. And once we know that HL0 clusters are close to disks, we can look at fluctuations around the disk's shape. And this is just to remind you of the definition of the model. We are still in the IID case, so there is no feedback, there's no alpha equals 0, and we're composing IID conformal maps. So these results tells us that if you embed the process in continuous time by simply making it piecewise constants, that will give you a Cadillac function in time. T here has the same role as before. And you take your random map phi n, and you subtract its first order approximation, which is the shape theorem. Now this difference is going to go to 0, so you have to blow things up in order to see something non-trivial. And the right size of this normalization factor is square root of c, which, just to remind you, is the size of the diameter of the particles seen in the pre-image of the cluster. Now, if you rescale this way, then you get a sequence of analytic functions outside the unit disk. And if you see them as functions both of z and time, you get a sequence of Cadillac processes with values in the space of holomorphic functions outside the unit disk. And what this theorem says is that as c goes to 0, these processes converge in distribution to a Gaussian process in the space of holomorphic functions outside the unit disk, which is conveniently described by this explicit stochastic partial differential equation. And just to tell you what this f looks like, it's a holomorphic function. So you can think of expanding it in Laurent series, and you just describe the Laurent coefficients, which will be random variables. And well, there will be functions of time, so there will be random processes. And it turns out that these are independent random processes, which are Gaussian. They are simply Ornstein-Uhlenbeck processes with a mean reverting speed k plus 1, which depends on the Laurent frequency, the Fourier frequency. And so in particular, as time goes to infinity, they have a stationary distribution. Each Laurent process converges to a Gaussian random variable with an explicit variance, 1 over k plus 1. And what this tells us is that well, there is a stationary distribution as t goes to infinity for this process. And if you look at the boundary values, so if you send the modulus of z to 1, well, the variance at each point explodes because 1 over k is not a summable series. And it explodes logarithmically. And in fact, the boundary values of these random fields are a logarithmically correlated Gaussian field, which is known as the augmented Gaussian free field. It's a close relative of the Gaussian free field, and the augmented word refers to the fact that there is a plus 1 here, rather than just having 1 over k. Okay, so just to give you a few quickly, just the idea of how these results are proved, scaling limit and fluctuations. Well, you have your map phi n and you would like to show that it's close to a deterministic map. So you have to understand how this map changes under one particular arrival. So you look at the difference between phi n and phi n minus 1. And well, phi n is just the previous map at a location which is not z, but it's been perturbed by the arrival of a new particle. So you can think of Taylor expanding, and then you just use the explicit expression that you have for the map that grows one particle to get to this approximation. And now you can work out, well, the drift that comes from this expansion, from this approximation. So you look at the expectation of this increment given fn minus 1, given the history up to time n minus 1. And this is something which is explicit. You can compute it explicitly. When you integrate this with respect to theta, you get 1, and so the drift is just that. And you can put these things together. This tells us that phi n should be compared to phi n minus 1, but evaluated at a point which is not z, but z slightly pushed out away from the unit disk by e to the c. And if you do that, you get something which is roughly a martingale increment, apart from errors in the approximation. So you compare your map to a deterministic map that simply grows a disk, and that's roughly a martingale, apart from small errors. And we know how to control the size of martingales. We want to show that the size of this term is small, this goes to 0. And well, we can control the size of a martingale via the size of its quadratic variation. And this is a computation that we can do explicitly, provided we have some information on our function phi n. So we make an ansatz. Let's say that the map phi n has been close to the map that should approximate it. And as soon as it goes far from it, meaning that the error in L infinity norm exceeds some given delta that we have to decide, we stop the process. So we introduce a stopping time, which tells us the error has become too large to stop. Or if this doesn't trigger, then we stop when we have aggregated enough particles. When the number of particles we want to aggregate is some constant over little c, which is going to infinity. So up to the stopping time, we can control the size of the martingale because we have information on the error that we make in approximating the map with a deterministic one. And well, if the size of the martingale turns out to be small enough, if the size of the martingale is smaller than delta, which is here, then that tells us that well, this stopping time is in fact equal to T over C, meaning that this time here didn't trigger. The error never became larger than delta. And so this estimate actually holds up to the number of particles we want to aggregate. So this is the idea behind the shaped theorem. This is not the original proof. James and Amanda were working with the inverse functions. This is a more modern proof. And for the fluctuations, so this is a more modern proof which is presented in our recent papers. And for the fluctuations, well, again, you have a martingale apart from small error terms, and you just have to control a bit better the quadratic variation of the martingale. If you show that it converges in probability to something deterministic, then you can use standard martingale central limit theorems to prove that the random field goes to a Gaussian field. Okay, and so this was the case alpha equals 0 when there was no attempt for compensating for the conformal distortion, so IID maps. Now, as soon as alpha is positive, as soon as alpha is non-zero, really, you have this complicated factor here, which makes the analysis hard because now you're touching particles of random size, which depends on what happened in the process. And if you try to use the same argument, well, it breaks down because when you look at the expected drift, you have a complicated angle, then a complicated factor here in the integral, which you don't know how to control. You're trying to say something about the map, and here you have the derivative of the map, which is even worse behaved. But, well, the behavior of this map phi prime will depend on sigma, which, to remind you, is how far away from the cluster boundary you're looking at it from. So if sigma is large enough, still going to zero, but slowly enough, you can hope to run a similar argument to say that you still have convergence to disks. And this is indeed what Alan Sola, Amanda Turner, and Fredrik Wiklund did in 2013. So they proved that if sigma goes to zero slowly enough, this random factor here behaves roughly in a deterministic fashion. And if this can be approximated by a deterministic number, you're basically back to the IID setting. And so you can prove again a shape theorem of this form, where here now alpha is visible in the radius of the limiting disk, but you still have convergence to disks. And this is true for all alpha greater than or equal than 0. So in particular, it doesn't see any phase transition. It's also true for alpha equals 2, which we had in mind should correspond to diffusion limited aggregation. And this tells us that sigma is too large. We're looking at the boundary of the cluster from too far away, and we don't see the structure of the cluster in a sufficiently interesting way. And so what we did with James and Amanda is we tried to make sigma smaller and see what happened. And just to remind you, this was the discussion about the rate of growth on the cluster boundary, which depended on this parameter alpha, which was a product of two things: the attachment rate at a given location and the particle size. Now, you can think of trading a different attachment rate for a different particle size, meaning that you can adjust the exponents here in such a way that the sum is, again, what you want, but you're distributing the exponents differently. So you give up using uniform angles, you prescribe a different distribution for the angles to the end of having deterministic particle sizes. And this idea was introduced in a paper by Alan Sola, Amanda Turner, and Fredrik Wiklund. And these are what we now call aggregate Loebner evolution models, in which we try to compensate for the distortion by using attachment angles which are not uniform, but with a probability density which depends on the density of harmonic measure on the cluster boundary. And advantage is that now we attach particles of roughly deterministic size. So the exponent you get here is still eta minus 1, so you still expect similar behavior. Eta should play the same role as alpha. So this is just a technical modification of these models, which allowed us to perform the analysis. And so we proved that when sigma goes to 0, but slower than the diameter of the particles, c to the half, so that you see some averaged effect, the map phi n is uniformly close to a map that simply grows a disk around the origin with an explicit error. This is true in the small particle limit, again, for a large class of particle shapes, and as long as eta is strictly below 1. So in the subcritical case, in the subcritical phase, up to the critical parameter in which you expect the phase transition. And we also have a shape theorem at criticality. So that's what the choice of eta, which corresponds to the Eden model, except we have to take sigma to go to 0 bits lower than the diameter of the particle. It's c to the 1/3. So the diameter of the particle to the 1/6. And the diameter of the particle to the 2/3, because the diameter is c to the half. And in this regime, we can still see that our random map is uniformly well approximated by a deterministic map, which simply grows a disk. So this is at criticality, and everything breaks above criticality, which is good because that means something is really changing in the supercritical setting where we expect these results not to hold. And
excuse me, can I interrupt? Sorry.
Yeah.
I missed or didn't understand when you switch from the family of models with the parameter alpha to the family of models with the parameter eta. Can you explain a bit again what is the difference between these two?
Yeah, so with the alpha, you try to compensate for the conformal distortion by introducing random particle sizes. So the alpha is present here in the particle size component of this computation. Whereas with the eta, you try to compensate using an attachment rate which is not uniform anymore. It's not, you're not attaching according to harmonic measure, but you're attaching according to a power of the harmonic measure.
Okay, and you keep the particle size constant.
And you keep the particle size constant.
Okay, thank you.
And okay, and we also have a fluctuation result. We have to take sigma a bit larger for the fluctuations, but rescaling exactly as in the IID case, we see that we still have convergence to a Gaussian field, well, to a Gaussian process, which is again an Olsen-Uhlenbeck process in the space of holomorphic functions. But the parameter eta is visible here in the mean reverting speed. And you see that, well, if eta equals 0, you recover the result I discussed earlier. And as eta grows from 0 to 1, which is the critical value, this nice term becomes smaller and smaller. And as eta equals 1, it completely disappears. So in terms of the limiting distribution of these Gaussian fields as t goes to infinity, when we are strictly subcritical, when eta is strictly smaller than 1, we still see a logarithmically correlated Gaussian field on the unit circle, extended analytically. While when eta equals 1, the logarithmic correlation completely breaks. And the Laurent coefficients just become IID. There's no dependence on K anymore. So the field becomes rougher. Okay, and let me just close by saying that we introduced two parameters, alpha and eta. We started with alpha and then we moved to eta, but you can think of working with both parameters being non-zero. So you get a two-parameter family of models. And the results I discussed apply in this region for eta below 1 and at 1. But in a subsequent work, we extended these results in the whole region where alpha plus eta is at most 1, which is really the value that matters for the growth. It's just the sum of these two exponents by the computation I showed you. Sto facendo il seminario, scusami. Okay, and just to point out that this applies to the hidden model, meaning that when alpha equals 2, we are in the physical case, and we can adjust the parameter eta to make alpha plus eta 1, just take eta to be minus 1. And we get a shape theorem and fluctuation result for the hidden model. And okay, these are the results when both of the parameters are switched to non-zero. It's a similar result. I think I'm out of time, so I'll probably skip those. And open questions. Well, in the hidden model, we don't expect Gaussian fluctuations. We expect KPZ fluctuations. That means the regularization is still too strong. So can we lower the regularization to see KPZ fluctuations? What happens if the initial shape is not a disk? The analysis here uses heavily the rotational invariance. And if the initial shape is not a disk, that's not available anymore. So what happens there? What happens if sigma is so low that you see a single particle arrival and not just an averaged effect? This is completely out of reach. And another thing which is out of reach is what happens when we grow according to a positive power of the harmonic measure. So alpha plus eta is greater than 1, which is this region here, where you do not expect a shape theorem and a fluctuation result. Okay, and I'll close. Thank you very much.
Thank you very much, Vittoria, for the very nice talk. So we have some time for questions, if there are some before James's talk. So maybe I can begin with the question actually. So the results that you presented, they were mostly about kind of what happens outside of this domain that's kind of growing. And you mentioned that there was some Amanda and James proved this something in terms of the internal structure of these fingers and gaps. This is kind of what happens on the inside. I was wondering if it's interesting to, or if it's known or interesting to ask somehow what happens to somehow the global shape of the holes inside. Like, do they quickly fill up? What's the diameter of the largest gap somehow?
Yeah, so this is something that James and Amanda also looked at in this paper actually. So they have they showed that you can't have gaps which are larger than c to the some power. Now I forget the power, but they have a power. And so that tells you that there are no macroscopic holes, and in fact there are no holes larger than a given size.
Okay. Maybe I have another question then. So do you have then? So you said for eta bigger than 1, essentially nothing is known, even for alphas say 0. But do you have a guess of what the sigma should be, what the scaling exponent should be?
So
how big it should be?
I'll show you. So this result by Alan, Amanda, and Frederick applies to all alpha. So that tells us that sigma goes to 0 slowly enough. You just see disks. And so this at least gives us a rate at which we have to beat, meaning that sigma has to go to 0 faster than this. But no, I don't really. I mean, the physical regime which you would like to discuss is the c to the half, which is sigma is roughly the diameter of the particle, in which you see one particle arrival. And we got close to that in our subcritical case because we said as soon as sigma is larger than c to the half, you have a shape theorem. So that's optimal in a sense. Okay. And I guess, well, it would be very nice to say something in the same regime in the supercritical case, but we don't even know what result we should prove because you don't expect a shape theorem. So you prove convergence to what? Which kind of shape? It should be a macroscopically random shape. We have no good description of it.
So there was some of the results that you had with like c to the 1/3 and things like this. Like this one, you expect that you could still hit 1/2 here somehow? That's
a good question. It's unclear whether this 1/3 it's just a technical wall or whether there's something which really happens. I think so. The shape theorem should hold down to 1/2, but the fluctuations should become should change behavior when you go to the c to the 1/3. The fluctuation result that we have doesn't hold at c to the 1/3. We need a larger exponent, 1/5.
And do you think that's also, it's just not true at say 1/3 or 1/2, or?
So one of the open question is whether at eta equals 1, you get KPZ fluctuations by taking sigma smaller. And we're debating on the right exponent of sigma, which might also depend on where you look for KPZ, meaning if you try to zoom in close to the class, or if you look at global fluctuations rather than local fluctuations. It should depend on also the choice of the state variable, but it's unclear whether C to the 1/3 it's the right exponent to see KPZ. We're not there yet.
Okay, thanks. Are there other questions for Vittoria? Okay, if not, actually it's already 4, so we can move directly to James' talk. So let's thank Vittoria again for the very nice talk. Yeah, thanks.
Yeah, I'm in the process of sharing my screen.
Sure, no problem.
You got it?
Yes, we can see it. Great. Should we?
Shall I? Yeah.
Sure. Yeah, sure. Yeah, I guess we have a few minutes break, so we can. Okay, so well, welcome back. So we're very pleased to have as the second talk today James Norris, who will be speaking to us about the analysis of stochastic evolutions in infinite dimensions with applications to stability of the Hastings-Lebedev models. Thanks.
Thank you. Thank you very much, Ilya and Julio, for the invitation to talk about this. So this is very much a second part to the talk which Vittoria has just given. And I'm going to focus to some extent on the methods that we had to use to analyze the ALE alpha eta models. So just to recap, the objects of study, and one little shift I'm going to make is to put the process into continuous time from the outset. So we'll be looking at a continuous time Markov chain. The state variable is a conformal map from the exterior disk, all the complex numbers with modulus greater than 1, into a subdomain of that exterior disk, and it evolves as follows. So you're sitting at a particular conformal map, phi, say, and that determines, according to a certain formula, a rate at which you get an arrival at a point theta on the unit circle, or e to the I theta on the unit circle. If you happen to choose a point theta, then you move your map phi to a new conformal map, which is phi composed with a particular single particle map, which attaches a particle at theta, and it attaches a particle whose size, or whose sort of capacity, is also a function of theta. Okay, so this is the same process which was described in Vittoria's talk, except that she was looking at the process. She looks at it jump by jump, the sequence of values that it takes, and it's natural in a way to put it into continuous time, both because we're going to take a continuum limit, but also because you don't have to normalize the rate divided by the integral of the lambda. Okay, so what are the given what's the given data for this family of models? Well, it's a couple of parameters, alpha and eta, which Vittoria discussed already. And we use those in defining the capacity C and the rate lambda. The size of the particles added at angle theta will be a parameter C, which is going to go to 0 times the modulus of the derivative of the current map at e to the I theta, or e to the sigma plus I theta. That's that regularization parameter that Vittoria discussed already, to the power minus alpha. And then sort of similarly, the rate is not C now, but C to the minus 1 times that quantity to the power minus eta. So we have to sort of take as a given a family of single particle conformal maps which add just one particle, and the particle will be small, so it'll have a small capacity, little c, and so it'll look like this this form here. C is small, so it's a sort of small perturbation of the identity map. The identity map is the conformal map which corresponds to the unit disk itself. But particular sort of example families for these maps might be small disks of area proportional to C, or sticks of length square root of C up to some universal constant. But the particular single particles can be quite general. The limits that we look at end up being insensitive to the particular shapes of particles. Okay, now Vittoria has already discussed. I mean, why would you choose to make the dynamics depend on this derivative phi primed? It has a geometric interpretation, which Vittoria already explained. It tells you what the I mean, there are two natural measures on the boundary of the cluster. There's the arc length of the boundary, and there's the harmonic measure. In the formulation we're using here, using conformal maps, the harmonic measure is a sort of very natural thing, because it's just the theta parameter on the circle, and if L denotes the arc length, then this phi primed is just telling us the ratio between these two measures, the Nicotin derivative of arc length with respect to harmonic measure. Okay, so we're using that quantity to adjust the size of the particles that we add, and as Vittoria explained, taking alpha equals 2 is the adjustment to the model which should give particles of roughly equal size in the cluster model. Taking eta equals 0 should give you then a DLA type model, and taking eta equals -1 should give you something like the Eden model. There are two minuses there. Okay, and in all the cases I'm going to discuss, the initial state will be the unit disk. So the initial conformal map will simply be the identity map. Okay, so here's a bit more about the model. So just recapping here what I just said. Here are some pictures illustrating the previous discussion. So the single particle maps here, f of c and theta, the dependence on theta is just this conjugation with respect to rotation that was explained before, and the little particle that gets added is something of diameter of order root c. And then it turns out, I mean, so this is just a finite rate Markov chain. So after a certain time interval, you will have composed a finite number of these maps together. Each time you compose a map, if for the next step, you get a theta which comes from the rate, and you might want to add a new particle, and then what you do is you first of all apply the f map which adds that particle, So that would look like this. And then you apply the old phi map to what you have here. And so this will probably end up sort of sitting out here somewhere. So the cluster grows particle by particle. It doesn't sort of change all the time. And over time, you'll get a complex picture emerging. I've drawn the picture here without too much distortion, which is a bit misleading. There is distortion going on. The distortion should be minimized by taking alpha equals 2. Okay, so with the normalization at infinity, the domain is in one-to-one correspondence with the conformal map. And so, of course, similarly, the complement of the domain, which is the, this here would be, this cluster after a certain length of time would be a kind of simply connected compact set in the plane, and we call it KT. And I guess the object of study is to understand, what does KT look like when C is small and when sigma is small. Okay, so just jumping straight away to a kind of a guest. Let me get rid of that. Maybe I'll just do that. So this is the conjectured limit for these models. This is a type of Loevner-Kufarev equation. So there's this theory developed by Loevner and Kufarev to describe continuously growing simply connected compact sets in the plane, or they were probably sort of looking at it from the other side, looking at the domains, the complement of the compact sets. But it's a particular Loevner-Kufarev equation. So usually one has an equation like this, but here you have a prescribed driving measure, which is a given quantity, a given family of measures, and that describes kind of in a distributed way how you're adding capacity to the cluster. And you keep on adding capacity, the cluster keeps on getting bigger. So I've made a loop here where the driving measure is now depending on the current state. Now, if you're given the driving measure, then you can solve this equation for phi, and that's all understood. So for one-to-one correspondence between growing compact sets and driving measures, but it's less clear what happens if you say it has to be sort of self-driving, so that the driving measure comes from the current map. Okay. Now, formally, this equation should describe the limiting evolution for a wide range of planar Laplacian growth models. I've not said what, I mean, this word Laplacian growth models is used. They're models which are constructed from to my mind, they're models where this quantity is kind of used to drive the dynamics. It's using the harmonic measure and the arc length to work out what the dynamics should be. Okay. This whole family should be described in the continuum limit by this LK zeta equation. If zeta equals 2, this should correspond to DLA, and zeta equals 1 should correspond to Eden model. Dielectric breakdown model would be the interpolating family between those two. So here are some things which are, well, some things which are and which are not known. If zeta equals 0, it becomes very simple, and there's the solution. If zeta equals 2 and sigma equals 0, this is in fact quite a well-studied object. It's the conformal map giving the Healy-Short flow. has a nicer structure than in general, because this driving quantity here can be written algebraically. So that's been quite extensively studied. But apart from these two cases, it's really not been studied at all, at least to my knowledge. Here's the equation again. So a PhD student here in Cambridge worked out that, excuse me, he could adapt the zeta equals 2 arguments to see that, in fact, you have local existence and uniqueness for the equation from analytic initial data. Ollie McIntyre. In general, one can spot solutions to the equation. So if you do a trial solution, which is a growing family of disks, the equation just becomes this, this simple ODE, which you can solve. Sorry, the pause there was my yes. So we call these disk solutions. It doesn't tell you how you can evolve from an arbitrary initial data. And it doesn't say that these are the unique evolutions from a disk initial data, but they are solutions. What we expect from various investigations is that the equation will behave well and will determine dynamics for zeta less than or equal to 1, but the equation will not capture completely the right dynamics when zeta is greater than 1. Now, one can think of the ALE alpha eta models as simply as some sort of, I mean, if you were primarily interested in this model as a limit model for growth models, then you could take ALE as being just as a way of investigating these equations by doing some kind of stochastic discretization. Of course, you need a limit theorem to say that they converge back to the solutions of the equations, which we don't have. But the ALE models are a natural way to discretize the dynamics. And the ALE models are elementary objects. They do exist. They can be simulated. One can study their behavior computationally, whereas these equations are in general not very well understood. So our guess is that this equation will describe the scaling limit for ALE alpha eta in some generality, provided we're in this subcritical regime, and even if one doesn't start from a disk. On the other hand, by simulating ALE computationally, and of course there's an enormous library of research out there in simulating growth models, which demonstrates that you see fractal behavior in supercritical regimes. So it's clear that a deterministic equation does not properly capture the dynamics when zeta is bigger than 1. Okay, so this is a recap of theorems which Vittoria stated more precisely, but I've just condensed it down to its sort of very rough level of description. If I take an ALE alpha eta process and let KT be the compact sets associated with it, and I suppose that the sum of the two parameters, the alpha and the eta, call it zeta, always will, is less than or equal to 1, then in the limit as C goes to 0 and sigma goes to 0, with these constraints here, it should be sigma should be greater than or equal to a power slightly less than half of C when zeta is less than 1, and similar with C to the 1/3 when zeta equals 1. Then the compact sets are approximately disks, and they're disks of this radius e to the tau t, where tau t comes from the disk solution of the LK zeta equation. And then with a slightly stronger hypothesis on the regularization, we can show that the fluctuations of the conformal map around the disk solution, which you rescale by the square root of C, converge weakly to a Gaussian limit. The Gaussian limit depends on alpha and eta, although the evolution here just depends on zeta. Okay, so that's the theorem, and I'd like to say something about the techniques that we use to prove it. Okay, so I'm going to move to much more general framework just for a little bit, hopefully to make some things clearer. Imagine we have a continuous time Markov chain, a finite rate Markov chain, and has a state space E, and it jumps from X to Y at rate lambda of X and dy. So it's an elementary object. What we should imagine is E is a vector space, and the jumps happen very fast, and the jumps are very small. And one often in this situation wants to describe X approximately by the solution of a differential equation. So let's suppose we have a candidate differential equation. So that means specifying a vector field which drives a differential equation, an ODE, in a vector space. Okay, so what I want to advertise is a way of decomposing the difference between the solution of a differential equation and a Markov chain, which is especially well adapted to the case where the vector space E is infinite dimensional. So this is the formula. If we jump down to it at the bottom, you can write the difference as a sum of two quantities, one of which is sort of martingale type. Notice it's not actually a martingale because this t is the same as this t here, but it's the value at time t of a martingale. And the quantities that enter the formula here are, on the one hand, the linearization of the ODE dynamics along the limit path. So if you have a small perturbation by Vs of the dynamics, how do you expect the solution to change at time t? Well, you work it out by solving this linear equation. So this line here is to define a linear operator in finite dimensions, just a matrix, which P acts linearly on V to tell you if I perturb the solution at S, how does it change it at T infinitesimally? So for a Markov chain X, the jump measure is just the empirical measure of jump times and values of the Markov chain, and then the compensated measure you get by subtracting lambda of x t dy dt. So that's a quantity that if you integrate previsible processes against, you get martingales. The drift beta, I should have written what this is. So beta of x is just the integral of y minus x against lambda of x dy. It's what you would guess that the drift of the Markov chain would be. Anyway, so in general, this decomposition holds, and the reason this is good in infinite dimensions is because you don't really need to know very much about the limit path. It's just that it solves the differential equation. You have to somehow get hold of the behavior of the linearized map. But then that's all you need to know. You don't even need to know that the differential equation is well posed. Just a kind of some sort of linear stability around the limit path will be enough. Okay, and this is the decomposition that we use to understand the fluid limit behavior of the ALE processes. Okay, so the process ALE has been described it's an evolution of conformal maps. In order to do some analysis and prove some limit theorems for it, we have to kind of think carefully about what space we want to work in and what norms we want to use on that space. So a good thing to do a good way to sort of decompose the ALE process is to say, well, the particle at time t will have a capacity, t of t, and then this phi hat map is like so that's kind of a normalized map. It has capacity 1. It's analogous to the Schlicht functions, which are studied in complex analysis, and so it looks like this. And so what I'm going to do is take as my state variables the tt and this function here, which is a holomorphic function, which is bounded at infinity. Okay, for norms on this, so I mean, it's not problematic to work out what norm you take on the t, because that's just a scalar quantity. But how should you measure the distance between the psi maps? Well, these are the good norms. We're going to integrate phi around a circle of radius r and look at the LP norm. And this has some, perhaps initially surprising properties, which come from the fact that with analytic functions, you can compute the function as averages. You can get a bound on the supremum of the function from the LP norm just by moving the value of the circle that you're looking at slightly. And notice that the bigger the p that you take, the smaller the adjustment you have to make. So large p is good. You can also get control of the derivative. I mean, for a holomorphic function, you can control the derivative in terms of the map itself. Again, just by slightly changing the radius of the circle you're looking at. I'll use this notation several times, that D is this variation of the derivative where you multiply by Z. So D of phi psi is Z times phi psi primed of Z. Okay. So I want to bring in one more ingredient to the recipe. So this is again sort of starting again. Suppose I have a certain sort of linear operator on my functions psi of z, which when I write, so I mean any holomorphic function bounded to infinity has this Laurent series. I suppose the operator m acts on psi diagonally in the Fourier basis. So, right, I mean, these are eigenfunctions of the map M. Okay, and for example, that map D, which I defined a moment ago, is a multiplier operator. These are called multiplier operators, and it's straightforward to see that these work very nicely on L2. These for these two norms with integrating around a circular radius r. It's not so clear, but it's a classical result called Marcinkiewicz multiplier theorem that with some slightly stronger hypothesis on the coefficients, namely that the first coefficient is bounded by a constant, and then somehow the kind of total variation of the sequence is also bounded by, say, the same constant. Then, in fact, you get a direct analog of the L2 result, saying that the operator norm of M on these spaces, PR spaces, is just given by this formula here for some constant c depending on p. This isn't the best. This isn't the best condition. You can sort of block the sum into geometrically growing subsums, and each of those needs to be bounded by a constant. But this is the simple one to use, and this holds in all the examples that we need. So there are good techniques to bound the LP norms of multiplier operators. Okay, so if you remember the interpolation formula, the general interpolation formula, and imagine trying to apply that to the ALE processes, and trying to show that the ALE processes converge to disk solutions of the LK zeta equation. So then the vector field is this one here. And we have to compute the linearized equation. So we have to consider solutions of the linearized equation around disk solutions. Now, although we know virtually nothing else about these LK zeta equations, we can compute that linear operator. And it turns out, because of the symmetry of the disk solutions, to be a multiplier operator. So Q is like one of the M's from the previous slide, and the multipliers for Q are given here. So the multiplier on the kth Fourier mode is K times 1 minus zeta times e to the minus sigma K plus 1. Okay, so if I then look at semigroup, which is generated by this multiplier operator, of course, that's again going to be a multiplier operator. The multipliers will be now e to the minus tau times qk. And what we end up using is some estimates on the composition of D and these p taus, which come out of the Martin-Kiewicz theorem. Of course, D and P will commute. So it doesn't matter which way around you put these operators. Okay, so in trying to estimate the terms in the interpolation formula, we need to estimate this linearized operator PTS, and are able to do so because of the multiplier theorem. Okay, the final ingredient for the kind of shape of the theorem, shape of proof which we adopt, is to bring the LP multiplier inequalities together with LP estimates for martingales. So, I mean, this is a kind of classical result from probability, that if I have any martingale M, then I can control its maximum process in LP in terms of the P over 2 norm of the quadratic variation. This is the previsible quadratic variation, and the P norm of the jumps, the maximum of the jumps. I can make the quantities that appear here, so that's what the notation means. That's the supremum. This is just the supremum of the jumps. To make the right-hand side of this equation a little bit more explicit, a nice concrete framework for martingales is when you construct them using a Poisson random measure, or a compensated Poisson random measure. So suppose H is a previsible process, and we have a compensated Poisson random measure, and suppose its intensity is of this form, so it's kind of constant in time, and has some sort of intensity measure in the state variable y. Then the objects appearing on the right-hand side in Berkeler's inequality are they have straightforward formulae in terms of the h and the lambda. Okay. So let's go back to the interpolation formula, and sort of think of it in a case where the state space is infinite dimensional. To be a bit concrete, let's imagine that the state space is a set of continuous functions. It will be in our main example, which is where it's functions which are holomorphic outside the unit disk, bounded at infinity. So imagine that our Markov chain, right, and so the states of the Markov chain are now functions. And let's suppose that, just to introduce some notation, let's suppose that x jumps by this function, delta of x and theta, at a rate lambda of x and theta d theta for all thetas in 0 to 2 pi. Now that's not much of a restriction on any kind of Markov chain in continuous functions, because the dependence on theta has not been specified. But you can see it's moving it a bit closer to the framework that we've got for the ALE processes. Okay, so then suppose we have some sort of candidate for a fluid limit, which is this vector field and the solution of the differential equation. Okay, so just to kind of introduce the jump measure again, the jump measure is this measure mu, and so this formula says what mu does. X starts at x naught, and then mu comes along and it proposes times at which the process will jump and theta values which are going to drive the jumps. If a certain theta value is chosen, then we make the jump delta depending on the current state of the process and the theta value which is chosen, and we jump by the function which that is then prescribes. So in the conformal map model, what will happen is that the delta of phi and theta will be phi composed with f of c of theta and phi and theta, and then subtract phi. So that's the jump that the conformal map makes. Okay, so then this is just rewriting the interpolation formula. This is the jump in the process. The mu tilde will just be the compensated version of this Poisson random measure now. Okay, and so in analyzing the ALE processes, we are faced with getting some good estimates to show that these two quantities, m and a, are actually small in the limit that we're interested in. Okay, so here's how everything comes together. So Burkholder's inequality applies to scalar martingales, right? But we can get a bunch of scalar martingales simply by evaluating the martingales here at fixed points in fixed z values. These will be complex numbers with modulus bigger than 1. And it's important to sort of take the same p. So we're going to use the same p in Burkholder's inequality as we end up using in the multiplier estimates. And of course, Burkholder's inequality gives us some estimate on the LP norm of the martingale, but I'm going to not only integrate with respect to omega, but also integrate with respect to the z variable. So I'm looking at the LP spaces with respect to the functions. And by choosing the same value of p, I mean, you can do this calculation whichever order you like. You can, take the LP norm in omega first, and then in E, or the other way around. So that's just some notation for that kind of big LP norm. So if I take Burke-Hölder's inequality for each Z, and then I integrate it, or take the LP norm of it, then I get something which looks very much like Burke-Hölder's inequality for this vector valued case. And I'm not going to go through what happens with all the terms, but I want to look at what happens with this quadratic variation term. Now, for the so I'm still working in the framework of the slide just before. So maybe just recap that. I've got this general Markov chain in a function space, and it jumps at a certain rate to a new function. Then the quadratic variation, and you also need the interpolation formula, which is here. So I'm taking this process, which is a martingale as a function of u. There's something slightly confusing here. That if I put t here, of course, mt, the t would appear twice. It appears here and here. This is a martingale in u, but if I put t here, it's not a martingale in t because the PTS depends on t. Okay, so I'm going to use the formula for the quadratic variation that I wrote before, and that will give me an identity for the quadratic variation at a particular point in space. But now I have here this operator that comes from the linearized dynamics for the candidate fluid limit. I can come along and take a LP over 2 norm of the quadratic variation, which is what I need to do in the Burke-Hölder inequality, and this gives me something that I bound like this. But now, I mean, suppose that all the rates are bounded by lambda star, and all the jumps are bounded in LP by, or all the jumps are bounded by delta star. Then I end up being able to separate use estimates on the linearized operators here, and then I get an integral over the jumps and the rates. And in the case of the ALE process, the rates are roughly of order c to the -1, but then the jumps are of order c, but the jumps get squared. And the Martinkiewicz estimates allow to control very nicely these operator norms, so that altogether we've got something here which is of size c, so that will be of size the square root of c when it comes back up here, and we're allowed to see that the martingale part, at least in the interpolation decomposition for the fluid limit, is small. Okay, my list of things still to do.
Excuse me if I
Yes.
may ask, because maybe I got lost, but how do you, I mean, these are all estimates, given that you have the knowledge of B, the vector field. correct? Or
Yes, we kind of have guessed the answer. We've guessed a B, and okay, I think I can answer your question best by looking back at this. So the Markov chain is giving you its drift. Now, in the best situation, you will choose the B to be the same. It's the same function.
Okay.
So then this is the difference between B of X, beta of X, and B. So B of X and B of X. And then what you've got here is the first term in the Taylor expansion for this difference. So this should be of order X minus X squared. And I mean, this starts off at 0. There's something you can't help happening, which is the noise coming in from the martingale term. But we've seen that that's going to be sort of order the square root of C in our example. So this term is actually going to be even smaller order term of order C again, so squared. So you have to choose the beta to approximate. You have to choose the B to approximate the drift of the Markov chain.
Yes. Okay, I missed that part. Thank you.
No. Thank you for bringing it up, because I failed to mention it. Yeah, so that's how that works. Yeah, as I say, open problems that have some similarities to Vittoria's open problems. So I would really like to be able to understand the LK zeta equation, because it seems to me that this is an important equation. And the case when zeta equals 1, which corresponds to the Eden model, is one which I don't believe is even understood. And yet it should behave well. It should behave reasonably well. Particularly, suppose I start off that equation at some arbitrary shape and let it evolve. What happens to that shape? Do the shapes all converge to disks? I think this is all unknown. We'd like to understand the case when we take the regularization parameter to be the square root of C, as Vittoria mentioned. Of course, this becomes significantly harder because one needs to understand how then you get kind of order 1 variations in the size of the particles, and proportionally order 1 variations in the size of the particles and in the rates at which particles are added at a particular place. And one has to understand how to average that, which we don't at the moment. We'd like, as Vittoria mentioned, to understand fluctuation regimes which are not Gaussian. So far have not done that. Another range of questions that one can think of is, if now we look at the sort of fractal turbulent case when zeta is bigger than 1, the stochastic side says that you still see randomness in the scaling limit, right? So the large clusters of DLA do not look deterministic. So it cannot be that these are produced by a deterministic equation. The randomness has to come from somewhere. The equation is failing to capture the dynamics. I mean, this happens sometimes. But on the other hand, if you imagine a diffusion limited aggregation process growing continuously, so imagine you succeeded in understanding a scaling limit for DLA, and think of it evolving over time as it gets larger. This is a growing family of compact sets in the plane. So by the Loevner theory, it corresponds to a driving measure in the Loevner equation. What does that driving measure look like? How do you extract the driving measure from the domain that's so far grown? All that is unknown and intriguing to me. Be happy to answer any questions.
Okay, thank you, James, for the very nice talk. So yes, we can pass over to questions. There's actually a question in the chat from a few minutes ago.
Ah, sure. Can this be connected to SLE scaling limits? Well, there are a variety of ways which maybe Amanda knows even more about, that one can set up these ALE processes so that the ALE cluster looks like an SLE in some particular limit. So in that sense, I think yes, the whole apparatus of Loevner theory it's not an accident that it's present here as it is in SLE. In SLE, you have growth at one kind of like sort of one point on the circle, whereas in these models, the growth is everywhere. And if you set up your ALE models so that growth is concentrated kind of increasingly in one place only, then more or less the only thing that you can be seeing in the limit is an SLE. Or indeed, I suppose, you could have multiple, you have multiple arms of SLE from kind of having growth in a finite number of places.
May I just shortly add? So I missed, unfortunately, the first lecture, but could the coefficients psi and c and others be then connected to kappa, a general coefficient, say, from the SLE? Could there be any relationship between the two analyses? Because the equation differential equation is of the same type, I think. And you have the complex parts and...
Yes, so the kappa from SLE is a quantity which describes the relationship between the timescale of the differential equation, the Loevner equation, and the timescale of the driving process, right? And as you vary that quantity, you see markedly different behavior in the SLE. If the process is moving on a slow timescale, if kappa is small, then the SLE is kind of a fairly regular curve. Well, it's still it's not a smooth curve, but then as you increase kappa and you make the Brownian motion move faster and faster, it starts to do wilder and wilder things like touching itself and then space filling. I don't see a direct connection with the parameters here now. It's not that there's going to be some sort of map of a one parameter family from ALE into SLE kappa, but the way things. So the sort of limit that we're looking at, we're letting the intensity of arrivals go to infinity. The size of the particles goes to zero, but the intensity goes to infinity. So the limits we're looking at have growth everywhere. So they're not at all like SLE, unless you're looking at a particularly singular example. Okay, so I wouldn't expect a direct correspondence, though I know that some particular ALE examples where it turns out that the growth ends up focusing near a single point do give you SLEs. But some time ago, Amanda was on the call. She could maybe say something if she wants.
Thanks, it's clear. Thank you.
Thanks. Are there other questions? Maybe I have another one actually. So this general method that you described of controlling the difference between a Markov chain and this continuous dynamic, sort of deterministic flow that you expect to see in the limit. If I understand correctly, you use this to control this the deviation of these maps to the disk, well, to solutions to the LK equation. But you had this other statement about the result about the fluctuations. And I was wondering, does this general method actually is used there as well?
Yeah, so I omitted to comment on that aspect, but there is a comment to be made. So so on this slide, there's this decomposition of the difference in terms of a martingale term and an integral dt term. I argued, in fact, that the martingale term was the dominant one, because this ended up being of order square root of c, and then when you put that in here, this turns up roughly of order c, and c is going to 0. So, in fact, the only contribution, the kind of the next level of contribution to the difference here, you can cross off the a, and then look at the m, and then just replace everything that you see here, sort of by the natural thing to guess in the scaling limit. You can guess a limit for this. This is deterministic anyway. This is some kind of compensated Poisson random measure. So just replace it by a white noise of Gaussian white noise of the same variance. That actually gives you a formula for the fluctuations. And if you unwrap that, you get the fluctuations which Vittoria described in her talk. So that this description, and so in particular, you remember that the fluctuations had this mean reverting property. Well, if you look at this operator PTS, that's in fact a nice operator in the case we're looking at, because it's e to the minus tau q, where if I just take if I just take sigma to be 0, then we've got q of k is k1 minus zeta, and at least for zeta less than 1, you're going to have the kth Fourier mode being damped by e to them, but at a rate proportional to k. The mean reversion in the OU processes for the fluctuations somehow derives from these multipliers.
Okay, thanks. And but in the discrepancy with the c, so you need to take a larger, with the sigma, you need to take a larger sigma for the fluctuations. This is related to an estimate that you do here, or with the martingale part.
Yeah, so
earlier,
there's evidence here things are going to be slightly harder. I think it's a relatively long story. The various ways in which zeta equals 1 causes grief. So I won't.
Okay, thanks. Okay. Thanks. Are there any final questions for James or Vittoria? Okay. If not, let's thank James and Vittoria again for the very nice talks. Thanks. Okay, and we resume in 2 weeks from now. Okay. Thank you very much.
Thanks, Ilya.
Thank you. Thank
Ilya.
you.
Thank you.
Thank you, everybody.
Thank you.
Bye-bye.
Bye.